Yeah, like, oh, that person, yeah, I don't. Are you? Yes, because maybe many days also it's also. No, I think it's like a long time. Oh, then got it. She wanted. What? Mr. Green. You know, graphing. Minus me, Fridays. I don't even have, I have.
Yeah, let me talk about that. Fine, we'll need it by next week.
That's it. Folding.
All right, good morning, guys. Let me talk a bit about the calendar. So we can see what's coming up. We're going to be finishing up the rest of this big unit here, unit 4, this week and next week. So the packet that you just picked up has the notes for the next, the rest of the remaining of this, remaining days of this week and a little bit of next week. We'll have a couple days to do test review for the first part. So the first part is non-calculator. This will be just doing power rule. U substitution is going to be a big part of what we do, and that's basically the big idea there is chain rule for integrals. Okay, but we also need to start doing some calculator work, which I have that portion of the test scheduled for the following Wednesday. Now, this test will just be 3 free response questions, and we'll go through exactly what those will be so you can get practice for the 2 days. We'll have 2 review days just for that calculator portion. If you have a graphing calculator, I think that's best, or if you don't have one, I think it's great if you can get your hands on one. So EI 84, any of the 83, 84 would be great. I do have some that you can borrow, but it's best if you can have access to one. That way you can take home and practice, and the features that we need to be able to do for the AP exam. It's good to get practice with it leading up to the exam. Now, having said that, a lot of those things can be done on the 36 Pro, but it's just a bit more cumbersome. And there's ways around it, but it just takes a little bit longer and not as efficient. Technically, this is not on the approved calculator list for the AP exam, but it just really depends on whether your proctor tells you to put it away. So I see some students, being able to use this on the AP exam, but the approved list is this. I see some students take both calculators into the exam, and some things they feel more comfortable using 36 Pro, some they feel more comfortable using the graphing calculator. So that's another option as well. But yeah, there are things that it's going to feel a lot slower on this versus graphing calculator, just because this you can't see the graph, so you have to just look at table of values, and it's just harder to visualize. But it can be done. There's just, but I'll show both ways if you absolutely cannot have access to a graphing calculator. Okay. But that we're going to do a lot of that starting next Wednesday. Okay, so I'll send out a reminder today, see if you guys are able to start looking into, if you don't have one, start looking into purchasing one or seeing some if you can have access to one. Okay. So today I want to talk a bit about definite integrals. So the big picture is that we know how to find the antiderivative. We did that using power rule, and now we have to figure out that application-wise, we can use that process to find the area under the curve, or something that's area related. Okay. So I gave you 3 handouts. One handout is the main notes, and then this is a summary sheets just over this concept between derivative and integrals that I want to kind of briefly go over. And the third sheet is just selected homework problems that might be easier to do, especially if you have the graph in front of you. Okay, so let me just start off with this summary sheet. This is kind of like the overall big picture. We can come back and revisit this. If you feel like this is a little over your head, it's okay, because we'll continually kind of circle back and loop back and talk a bit more. But I do want to kind of give you kind of like the big picture and the connection between derivatives and integrals. So I talked briefly about this, how derivative is just another word for slope. It explores the rate of change, right? And slope is just change in y over change in x. And we found the derivative, we're able to find the slope of an ever-changing curve, right? And we know slope has the main operation is a division, right? Change in y over change in x. But if we flip that operation around, if we undo that division process, it turns into a multiplication process. And that x2 minus x1 times y2 minus y1 is just length and width, right? And x2 minus x1 is just some horizontal distance. Y2 minus y1 is some vertical distance. So if I multiply a horizontal distance times vertical distance, what I get back in return is something of an area of a rectangle. So that's why if we undo the derivative process, we get something that is area related. So that's the big picture there. Right, so derivative, the d of f of x over dx, the derivative of the function f of x evaluated at x equals a gives the slope of the curve at x equals a. Okay, and if I undo this process, right, turn this into a multiplication problem, then it becomes f of x dx, right? F of x dx, and this has an area kind of look to it, right? F of x represents the height, and then dx represents the width. If I put those together, we get something that's area related, area of a rectangle. Right? And we talked about how true that rectangles is not going to quite do the job of getting the area of a curved region, but if we think of it as infinitely thin rectangles, then we can accumulate all those and adapt to all the changes of the curve. So the integral over the range of x from b to a gives the area under the curve between those points. Okay, so today we're going to be moving towards the antiderivative function to the actual area of a region. Okay, so this diagram, these two diagrams, is going to kind of help demonstrate the connection. And I have the key on the back, so if you want to follow along on the back page, we can. So this is the function. Okay, so let's say this function is 3x squared, right? It's a parabola, right? And I didn't extend this parabola out, but if I did, it would have continued up. Okay. All right. I'm just showing this portion here. Right. Now, if I want to find the derivative of 3x squared, if I go through power rule, what's the derivative of 3x squared? 6x. Okay, so what 6x is going to do, it's going to help us find the slope of any point on this curve. Okay, and I put the 6x graph over here. Okay, so 6x is a linear graph, right? So this is somehow going to tell us the slope behavior of this curve. Okay, so we can do it algebraically. We can also do it graphically. Okay, so let's say I have an ordered pair 1, 3. I'm going to highlight that point here. And if I asked you what is the slope of this curve at this point, you would just plug 1 into the derivative. And what would the slope be at that point? 6, right? 6 times 1 is 6. So that tells us that at this point, there's a pretty steep curve or a pretty steep slope, right? That has a steepness of, exact steepness of 6, right? Okay. And so I can tell this by looking at or plugging into the derivative, but I can also find it from looking at the slope graph, right? F prime of 1 is equal to 6, right? That's a y value of 6, right? So I can get that information from the derivative function. I can also look at it from the derivative graph, right? Does that make sense? Right? F prime of 1 equals 6. I can look at it from here. I can also do it just by putting into the derivative. Okay. All right. There's another order pair here, 212. I want to use this to help make some connections here. That's just an order pair, right? If I plug 2 into the function, I get 12. Okay, so we know how this process works, right? It makes sense that this derivative is going to help us tell us the slope of any point on this curve. Now, the flip side is what we're doing this semester. Okay, so this semester, let's say we start off with this derivative 6x. Okay, if I took the antiderivative, right? If I went through power rule, what would that become? 6x power rule for integrals, 6x squared over 2, which becomes 3x squared plus c. Now, 3x squared is this, right? So this graph is now going to also give some information about this f prime, okay? And what this is going to do is that the area under the derivative graph is equal to the rise in height. Okay. Which one is that? Anybody? Thanks for Is there a second? Okay. So this f prime, we know that f prime of 1 is equal to 6. So let me put that here. And we know that f prime of 2 is equal to 12. Let me just put that here. Okay. So the integral of this function can be used to find the area under the graph. So I want to kind of show you this real quick, and we can talk about the details when we get to the next screen. What shape do you see here created between the graph and the line? Trapezoid, okay? So trapezoid is the area is 1/2 width, height 1 plus height 2. Okay, so the area is equal to 9. Okay, so how is this 3x squared going to do the work of finding the area of 9? Okay, so this is what this is going to do here. If I were to plug in the 1 and 2 into this 3x squared, okay, I would get 12 and I would get 3. So the change in height of the function is going to tell us the area under the curve. Okay, so this is how we're going to be working this problem, is that if we find the antiderivative, this 3x squared is going to tell us the area of under this curve, under this graph. Okay, and likewise, this derivative function is going to tell us the slope of this. Okay, so they both are kind of giving information about the other one. Okay, so the derivative tells us the slope of the function, and the antiderivative tells us the area under this graph. So the big picture here is that the area under the derivative graph is equal to the rise in height of the antiderivative graph. So the rise in height is from 3 to 12. 12 minus 3 is 9. That difference in height is 9, and that is going to correspond with the area under this derivative graph. Okay, there's more that I want to say, but I think for now, I just want to help us at least see that there's that connection between the two of them. Okay, so one is going to tell us information about the slope. The other is going to flip side, is going to tell us the area of the other one. Okay. So we're going to be exploring this, what we call this first fundamental theorem of calculus. And there's different variations of it. The AP exam loves to explore these. And so we're going to practice a lot of different variations and see things from a conceptual perspective, from a graphical perspective, from an algebraic perspective. Okay, so this is what we're working towards today and the rest of the week. Okay, so if we can go to the notes page or notes packet. Okay, so here's the first fundamental theorem of calculus. I abbreviated FFTC, first fundamental theorem of calculus. Okay. And here's what the rule says. It says that if I take the antiderivative of a function, it's going to turn itself into this uppercase f. And when we go through the antiderivative process, whatever function it turns into, that's the notation that we use to indicate the antiderivative of this process. And we did that with power rule over the course of the quiz. Another variation of this is integral from a to b of f prime of x. Basically, whatever we start with, it's going to rise up to the level above it. So f prime of x is going to turn itself into what? F of x, yep. And then what we do is we take the upper bound, whatever that value is, and then we take the lower bound, whatever that value is, insert it and subtract it. So basically, the height difference of the function is equal to the area under the f prime graph. Okay, so that's the big visual picture that we're seeing, right? The area under the f prime graph is equal to the change in height of the f of x graph. Okay. So recall that the general derivative is a slope finding function or formula from first semester. If I have a slope formula 2x plus 1, I can use it to find the slope at a point of the original graph. So likewise, this semester, the indefinite integral is an area finding function. So indefinite integral means that there are no bounds. Okay, so if there are no bounds, it'll just produce a formula. It won't give you an area value. Okay. Now the definite integral means that we're actually finding something that's area related, and that's when we're going to be involving bounds. If we go through the bounds process, we're going to come to a formula first, but ultimately in the end, it's going to give us a number, and that number is going to correspond with an area related value. Okay, I say area related because sometimes we may see negatives, and negatives is not what we associate with area. So right now we'll just say area related. We'll discover the full area formula a few units down the road, but right now just understand, okay, it's area related, and that's what's important. Okay. If a function is continuous on a closed interval, meaning that it's connected, it doesn't have to be a smooth curve, it just needs to be connected, then the function is able to be integrated on that interval. Okay, so let's go through this process here. Evaluate the definite integral from 1 to 4 of 3x squared plus 4x minus 1. Now, visually, what this is doing is that whatever this graph looks like, it's a parabola, between 1 and 4, we can find the area of this curved region. So whatever this graph looks like, let's say it looks like this from 1 to 4. We're trying to figure out what the area of that region is. Okay, so we're going to go through this process. And the bounds is going to help us give us a closed region, and we're going to find something that is area related. Okay, so we're going to go through this process. We're going to take the antiderivative, make that f that starting function rise up to the antiderivative level, and then we're going to work in the bounds. Okay. So something that's important is that we have to realize that we do not do anything with the bounds initially. Okay. I think a lot of students want to work with the bounds initially because typically we like to read a problem from left to right. So if we read the problem from left to right, the 1 and 4 is the first thing that you see. And so naturally, I think a lot of students want to just go ahead and insert into the function. Okay? But we haven't reached the antiderivative yet. The bounds are not ready for us to use. So what you want to do is, for now, okay, until you feel more confident with this process, go ahead and find the antiderivative without the bounds. Okay, so after we reach the result, then the bounds are going to take its role. Okay. So we're just going to pretend like we don't see the bounds. We have to get to the form. We have to get to the antiderivative first before the 1 and 4 can play a role. So every term is set up and ready for power rule. There's nothing hindering our process. So let's jump into it. So 3x squared becomes what? Yep, 3x cubed over 3. 4x becomes 4x squared over 2. Minus 1 becomes minus 1x, and then plus c. Okay, so that's how we would just stop here. I mean, we'll do some cleanup, but this is what we call the indefinite, right? The process of this indefinite interval. But we have the bounds to work with. Okay, so as we work in the bounds, one thing we have to realize is we're getting a number related value, and that plus c is going to wash itself out. So we can ignore the plus c. Okay. We're going to clean this expression up. So 3 over 3 goes away. What does the next term become? Yeah, 2x squared minus 1x. And now we're ready to work in the bounds. Okay, so typically, the notation that we use is we use a half bracket to indicate that we are ready to evaluate this expression with the bounds that's given in the problem. Okay, so this is sitting at the uppercase f of x level because we found the antiderivative, and then we're going to insert the upper bound first, minus then the lower bound. So that's the process we're going to go through. So the upper bound is going to get inserted into the expression first. So we're basically doing this. We're going to do f of 4 minus f of 1. All right, so now I'm going to just go through the process here. 4 inserts into all the x's. What comes after this? Minus, okay. Minus, and then we're going to do f of 1. Now, I think it's a good idea to always protect whatever comes after your minus sign with a big set of parentheses. Okay. That's a reminder that this negative is going to influence everything that comes after it. Okay, so now we're going to plug in what? Plug in 1, yeah. So 1 cubed plus 2 times 1 squared minus 1 times 1. Okay, I'll do the math for us here. This will end up giving us 92 minus 2, which is 90. So the change in height of the f of x, uppercase f of x function, which we do not see. Okay, we don't see that graph. But the change in height of that antiderivative graph is going to equal to the area under this original graph, this parabola. Okay. It's equal to 90. Okay. So that's the big idea. That's the big picture that we're going to be kind of practicing and seeing different variations of this process. Okay. Any questions with that? Okay, so another thing that I see some students wrestle with in terms of the process is that we always plug in the upper bound first. Okay, sometimes the upper bound may be a smaller value than the lower bound. We don't care about it. Whatever you see in the upper bound, you always are going to start with that first. Now, if you want to flip the bounds, we'll talk about it on the next page, where we can do that if we wanted to, but just remember, it doesn't matter which one is a higher value or lower value. If you just go through the process, the problem will work itself out. So whatever is here in this location is going to get inserted first. And the second thing I already mentioned is we do not use the bounds on the expression you see in front of you. We have to transform this into the appropriate antiderivative before the bounds can be used. Okay. And then finally is after you evaluate your upper bound, make sure you put a minus sign, but then a big parentheses is a good idea, so that we don't forget about that. This negative is going to influence everything that comes after it. Okay. And I also talked about this, how for definite integrals, we don't need to worry about this constant plus c. It'll always wash out. So we need a plus c if we don't see bounds, but if we see bounds, we can remove the plus c. Because if both of these produce a plus c, a c minus a c will just go away to 0. So that's why we can ignore that plus c. Both these processes that minus sign will take both those c values and wipe them out. Okay, so see if you can go through that process and apply the same process for number 2. Okay. Go through power rule, find the antiderivative first, set up your bounds. Upper bound gets inserted first, then a minus sign, and then the lower bound. Okay, what'd you guys get? You guys get a negative number? -3. Okay. So let me talk about that process. I talked about how it's area related, but it's not quite area that what we associate with area. And the reason why we're getting a negative number, and I think I talked about this before, is that it's the accumulation of the areas above and below the x-axis. So first 2x, we turn it into 2x squared over 2, and then clean that up, x squared. From 1 to -2, the upper bound gets inserted first, minus, then the lower bound, we get -3. And visually, what's happening is that a 2x is going to have regions above and below the x-axis. So this region will produce -4 because it's accumulation of negative y values. And this region will give us a +1. So because there's more of an area region below the x-axis, -4 plus 1 will give us -3. Just know that this is giving us something area related, but it's not the true area. Like what if we think of it as true area, we would just think this is 4 plus 1 and make it 5. But that process is not going to come until a future unit. Okay. For now, just understand that that's an accumulation of negative and positive of values, and whichever wins out is going to be the sign of your answer. Okay, next page. All right, let me go over some integral properties. So we're kind of stepping away from first theorem here. We're just looking at it from a visual perspective. Okay, let's say I had a graph. Let me call this f of x. So the definite integral from a to a, okay, let's say that a value is 2 or 3, it doesn't really matter. Okay. So we're starting at this point, but then we don't move. Okay, we go from a to a, meaning that we don't create any area, no width to begin with. So what that tells us is that if your bounds are the same, there's no area for us to find. So antiderivative is your definite integral value is always going to be 0. Okay, so if your bounds are the same, we don't have any regions to find, so your integral is always 0. Okay. So the second integral property here is if I want to find the definite integral from a to b of f of x dx versus the integral from b to a of f of x dx, if I were to find these two regions from a to b or from b to a, these will always be opposites of each other. Okay, so if one process gives you 5, the other process will give you a -5. So if I want to make them equal, I can just put a negative in front. So what that is saying is that if I want to evaluate a definite integral from -1 to 3 of f of x dx, but let's say, let me change this. Let me kind of show you an example when we would want to use this property. Let's say we're going from 3 to -1. Okay. And if you're trying to read the graph, you typically want to read the graph from left to right. So to make it visually easier to work with, we can flip the bounds and put a negative outside and still be working with the same problem. So I can always flip the bounds, change the order of my bounds, and as long as I balance it out with a negative, I'm working with the same problem. Okay, but sometimes adjusting the bounds can make it easier visually for us to work through a problem. So that's a good property to apply in certain situations. The third is, sorry, this negative is a stray mark. So there's no negative there. It's just integral. So it says the integral from a to b of f of x dx is equal to the integral from a to c plus from c to b. So what this is basically saying is that if I have a really large region that I want to evaluate, I can split that region into 2 smaller regions and then handle them individually and then put them together at the end. So let's say I have sorry. Yeah, let's say I had C in between and then B at the end. The integral from A to B is the same as taking A to C, find that region, and then do from C to B and find that region and add them together at the end. Okay, so sometimes it's in certain situations it's good, it's helpful to split a larger problem into smaller problems and add them together at the end. All right, so let me explore some of these examples that take advantage of these properties, where we can take advantage of these properties. Okay, let's say the definite integral from 0 to 3 is 4, and the integral from 3 to 6 is equal to -1. Find the below. Okay, all right, so it says find the integral from 0 to 6. So if I want to find the integral from 0 to 6, I can do what with these two? Add it, yep, because I know that 3 is between 0 and 6, so the definite integral from 0 to 3 of f of x dx plus the integral from 3 to 6 of f of x dx will total to be the integral from 0 to 6. Right? And this is equal to 4, that's equal to -1. We add that together, we get 3. Okay, let's practice this property here. This one's going from 6 to 3. I have an integral from 3 to 6. So what can I do to make this look like my property? Flip it and then adjust it by putting a negative. Okay, so I'm going to put a negative outside, integral from 3 to 6, because I know that these two are the same, right? I changed the balance, but I took a negative outside, so I haven't changed anything. Now let's evaluate this problem here, okay? What do you know about the integral from 3 to 6? That's equal to -1. So if I do a negative of a -1, that's equal to what? +1. Okay, for part C, I'm starting at 3 and I'm ending at 3. If my lower and upper bound are the same, my definite integral is always equal to what? Always equal to 0. Yeah. If I start and end at the same point, I haven't created an area for me to work with. It's always going to be 0. Okay. Put a star next to part D. This is misleading and easy to make a mistake with. The first thing I want to make sure that we understand is that this is not the same thing as this. Why are these not the same? So is this 3 independent? Yeah, this 3 is, right? Is this 3 independent? It's not. Okay, so this 3 is under this integral umbrella. So that 3 is not a 3, it's something else. Okay. So it's best to split this up into 2 problems. Right? So this we can handle with a property given, but this we have to go through what? We got to go through power rule. We got to go through our antiderivative power rule process. Okay, so let me continue breaking this up here. I can pull that -5 out so that I can kind of separate the parts that I want to work with. What's given to me here? The integral from 3 to 6 is equal to what? Equal to -1. If I replace that with -1, -1 times -5 is just 5. Okay, so I can put that off to the side. Come back to it when I take care of this. Okay, so now the second part of the problem, I got to go through a different process because it's not a function notation that I can use a property. What's the antiderivative of 3? Get 3x, right? We don't deal anything with a balance until we transform that 3 into its proper antiderivative. So once you take care of the antiderivative, it becomes 3x. Now we can work the bounds in. Okay, so the 6 and the 3 now has a role for us. Okay, what gets inserted first? Upper bound first. Okay, doesn't matter if it's a larger or smaller value, it's always inserted first. Then the lower bound. Okay, so 18 minus 9 is 9. And finally, we can add our results together. 5 plus 9. Okay, example 4. If the definite integral from 3 to 8 of f prime of x equals to 10 and f of 8 equals 6, find f of 3. Okay, so this is kind of a conceptual problem. I've seen this type of problem show up on multiple choice of AP exams. So I want to kind of show you how College Board likes to take first theorem and arrange it in a way where students to see if students can make sense of it. So reminder that first theorem can be used as an equation solving tool to find the value of an antiderivative at a specific point. So we know this is true, right? If I start out with f prime, I can make it rise up to f of x and then plug in the upper and lower bound. So what if I adapted this for the left side, right? Because we know that this matches this. So what if I replace a and b with 3 and 8? So we know that I'm going to ignore the right side for now. It's just going to work from what I know with first theorem. Okay, so I'm just working in my a and b value. Okay, so f prime is going to rise up to what? through this antiderivative process. F prime rises to f of x, right? Antiderivative of f prime is f. Then we can plug in what? What's my upper bound? What's the b value? 8. My a value is my lower bound, so f of 3. So we know this is true, right? The definite integral from 3 to 8 of f prime is f of 8 minus f of 3. The change in the y value of the original function is equal to the area under this f prime graph. Okay, so it says that this is equal to 10, so I can just take this piece of this equation, make it 10. Do I know anything about f of 8? 6. And now can I find f of 3? So 10 equals 6 minus f of 3. I only have one missing variable, which is f of 3. So now I can just rearrange it and solve for f of 3. So add f of 3 to the left side, subtract 10 from the left side to the right side. F of 3 equals what? -4. Okay, example 5. The area for each region is given. Okay, so 10, 2, and 3. Okay, find the definite integral from a to b. Now we know that anything above the x-axis is an accumulation of positive y values, but anything below the x-axis is accumulation of what? Negative y values. So the area is 2, but the definite integral here is really what? A -2. So if I want to add these values together, if I want to find the definite integral, this will be 10 minus 2 plus 3, which is equal to 11. Definite integral from a to c is a positive, from c to d is negative, from d to b is positive. I'm just I do want to help get you started with some of the homework problems that you're going to see. So on the third sheet that you picked up, so it says the graph consists of line segments as shown. Evaluate the definite integral using geometric formulas. If it was a curve like this, then the problem would have to tell you what the area is, right? Because we don't know what the shape is. We don't know what the area is. But these are shapes that are known, right? These are just made up of triangles and rectangles and squares. So we can just use geometric formulas to actually find the area between the graph and the x-axis. So we want to go from 0 to 1. So 0 to 1 is this little triangle region here. We know the area of a triangle is 1/2 base times height. So 1/2 1 times 1. What's the area of this little region here? Okay. 1 times 1 times 1/2 is 1/2. So we know this region is 1/2, but it's below the x-axis. So we know this is going to give us a -1/2. So the definite integral from 0 to 1, I can pull that negative out just so I can help me see this process here. So we know that this definite integral just from 0 to 1 will produce what? -1/2. -1/2 with a negative in front, that'll turn itself into a positive. Okay, part B. The definite interval from 3 to 4. I can pull that 3 out just so I can kind of separate the parts that I want to use the graph for. I can just focus my attention on this. Okay, definite interval from 3 to 4. 3 to 4, this is a rectangle. What is the area of that region? Okay, width times height. What's the area there? 1 times 2 is 2, right? So if I know that the integral from 3 to 4 is 2, what's my resulting answer going to be? Just 6. Yeah. Okay, definite integral from 0 to 7. So from 0 to 7, I'm going to go through and find each of these separate areas and then add them up. All right, so this is 1/2 base times height. These are both positive, but what do you notice about from 6 to 7? Below the x-axis, so this region is going to be what? Negative. Okay, so we want to go and find the area between the graph and the x-axis. So make sure that you're always looking at the region between the graph and the x-axis. We don't want to create different shapes that's not between the graph and the x-axis. Okay. So you flip to the next page here if you want to kind of see what I got here. So this is area is negative 1/2. This is 1/2 base times height. 1/2 2 times 2 is 4. 4 divided by 2 is 2. So this is also negative 1/2. So if I want to go from 0 to 7, I just add up all these values. Negative 1/2 minus 1/2 plus 2 plus 2 plus 2. So that's 6 minus 1. That's equal to 5. Positive 2.
So. So. Giving. I used to.
For the area under this graph, but we don't have the graph. Of use. And we know that from 3 to 6 equals -1. So therefore, from 6 to 3 must be equal to a positive one, because if the bounds are the only thing that's different, then my answer will just be opposite signs of each other.
Number 5.
You're, huh? No. Guys, I realized that this was not assigned in the homework, so don't worry about this.